Hello students. In our last class, we have started up with hydrogen bonding, types of hydrogen bonds, intermolecular and intramolecular. Also, we have studied anomalous properties of few molecules due to the presence of hydrogen bonding. In that, we have already finished some 4 molecules. Now, let me start up with the other molecule, that is the water. So, if you consider water, you have H2O. Consider the oxygen atom. In the same group in which oxygen is present, you have sulfur, selenium and tellurium. When compared to hydrides of all these elements, you have high boiling point only for water. Now let me explain what is the reason behind this in detail. According to spectral studies, it has been shown that the oxygen atom which is present in the water is bonded to 4 hydrogen atoms. So you have totally 4 bonds to which oxygen is linked. That is, oxygen is bonded to 4 hydrogen atoms. Total you have 4 bonds. Among these 4 bonds, 2 bonds are the covalent bonds and the remaining 2 are the hydrogen bonds. Let me represent that diagrammatically by showing the intermolecular hydrogen bonding in case of water molecules. That is, how intermolecular hydrogen bonding results in the association of water molecules. So you have oxygen H. Let me show this as the dotted line. Here you have one more water molecule H. Dotted line O H. So H2O, H2O and H2O. And this chain will continue on both the sides. I have represented by dotted line, means the chain is continuing on the both sides. Now let me link the water molecule to this oxygen atom. You have H, O, H. Again, here you show the linkage H, O, H. The same thing repeats here also. You have H, O, H. Now what I had explained you in the spectral studies, that is which were made by spectral studies, compare just with the structure. See, you have oxygen has 4 bonds. In that you have 2 covalent bonds and 2 hydrogen bonds. Look here, here you have oxygen atom which is linked to 1, 2, 3, 4 hydrogen atoms. In this, 2 are covalent bonds and these dotted lines will represent hydrogen bonds. You already know what is the condition for the formation of hydrogen bonds. A, H, B. You can compare while explaining the hydrogen bond. I have already told you there should be one electronegative atom which should be linked to the hydrogen. So it is in the same format. So between these two you have a covalent bond and one more electronegative atom should be there that should be linked to hydrogen and that will be your hydrogen bond. Correct? Again in this, here also the same rule applies. O, H, H. Here this is one electronegative atom, this is the covalent bond and between this hydrogen and oxygen you have one hydrogen bond. So totally oxygen is bonded to 4 hydrogens. Among this 2 are covalent bonds and 2 are hydrogen bonds. Now you can say that this structure will repeat in a 3-dimensional manner. In this, on the paper, you can just show the structure in the 2 dimension, but you cannot represent the 3-dimensional structure in a paper. So you have to imagine the same structure will continue in the 3-dimensional way. So this and all is happening due to the intermolecular hydrogen bonding. So because of intermolecular hydrogen bonding, water is showing high boiling point. Let me now explain How intermolecular hydrogen bonding results in high boiling point. Due to intermolecular hydrogen bonding, number of hydrogen bonds increases. Now, more energy is needed for breaking of bond. As number of hydrogen bonds are increasing, more energy is required for breaking of the bond. While explaining the bond energy definition, I had already told you, as the number of bonds are increasing, for the breakage of each bond, you need more and more energy. Correct? As the number of bonds are increasing, you have to apply more and more energy for the breakage of bond. So obviously, the boiling point of the molecule increases with the increase in the number of bonds in it. So this is the reason why water is having high boiling point when compared to other hydrides. The main reason is due to intermolecular hydrogen bonding. Now let me move to the next molecule, that is hydrogen fluoride. Usually any molecule which is dissolved in water, it gives H plus and F minus. But this is not possible in case of hydrogen fluoride. Instead, this forms HF2 minus. That is hydrogen difluoride ion. Hydrogen difluoride ion is formed when HF is dissolved in water, and this is mainly responsible for the formation of a molecule called as potassium hydrogen fluoride. This is the first point you have to remember in case of HF. The second thing is, this is having high boiling point. Again the same thing repeats as I told you in the earlier case, that is in the water. HF is having high boiling point due to intermolecular hydrogen bonding, that is number of bonds increases, more energy is required for breakage of bonds, and obviously the boiling point increases. 2 points you have to quote under the molecule HF. Now the last one which is left is the biomolecules. You can observe the presence of hydrogen bonds in many biomolecules like DNA, proteins, amino acids, etc. You can observe the presence of hydrogen bonding in many biomolecules like DNA, proteins and amino acids. Here under this, let me discuss by taking only two examples, that is the structure of protein and the structure of DNA molecule. Now let me start off with the proteins first. If you consider the proteins, you have two types of structure in it, primary structure and secondary structure of proteins. So if you are considering the primary structure, it is some straight chain structure you have. The structure is very simple and it is simply made up of amino acids, and these amino acids are linked together through the peptide bonds. They just have the amino acids. These amino acids will be linked up with the help of peptide bonds. That is the primary structure of protein. Before going to the second structure, you have to know one important thing about the structure of protein. That is, in general, the structure of any biomolecule. The structure of biomolecule determines the function of molecule. The function of the molecule is mainly determined by the structure of the molecule. So coming to the secondary structure is made up of many number of peptide chains, that is polypeptide chains are observed in case of second structure, and these polypeptide chains, how they are linked? They are linked through hydrogen bonds. So here the structure of the secondary proteins, that is the secondary structure of proteins, is quite complicated. Like you have in your primary structure, it doesn't have any simple structure, but the structure is quite complicated. It may have some twisted like or cylindrical or some helical like structures may be there in case of secondary structure of proteins. So mainly this structure of the protein is dependent on the presence of hydrogen bonds between the atoms. So you can say that indirectly the hydrogen bonding is helping to perform the functions of proteins. Since structure is the main thing which is responsible to perform the functions, so and this structure is depending on the hydrogen bonds which are formed between the atoms. So you can say that indirectly the hydrogen bonding is helping to perform the functions of the proteins. Clear? The second example let me take under the biomolecules, that is DNA. I think you already know the structure of the DNA. This DNA is having double helical structure, correct? So you have two twisted strands. I'll just represent it by drawing two simple lines. Don't get confused. So in one strand you'll be having adenine and the other strand you'll be having thymine, guanine and cytosine. This adenine is linked to thymine, guanine is linked to cytosine. In these two things, you can observe the presence of hydrogen bonds. That is intermolecular hydrogen bond you can observe between the two molecules, that is between adenine and thymine and guanine and cytosine. For this, for extra information, you can just refer my notes which I have already posted in the group. The structures of adenine, thymine, guanine, cytosine I have already mentioned, and I have also shown the linkage between the molecules. This double helical structure of DNA, it is responsible for three main things, that is for the synthesis of protein and RNA synthesis and also for the cell division. This double helical structure is responsible for protein synthesis, synthesis of RNA and also cell division. And I have already told that the structure mainly depends on how the bonds are present between the molecules. So you can say that hydrogen bonding indirectly helps the DNA molecule to perform all its function. This is the important properties of biomolecules due to the presence of hydrogen bonds. By this, we have finished the anomalous properties of different types of molecules and the hydrogen bonding. Now let us move on to another force, that is van der Waals force of attraction. In this you can observe that the bond between the two atoms, you can observe a covalent bond or a ionic bond or other bonds between the atoms. Now the atoms will combine to form the molecules. Let me take one general example. Let me take an atom A which is linked to atom B. Let me take this, the bond between the atoms A and B is a covalent bond. And let me take one more molecule. This bond between the atoms A and B is a covalent bond. Now these two molecules are linked together by a force of attraction. This force of attraction is nothing but van der Waals force of attraction. So here atoms are combining to form the molecules. Then these two molecules or many number of molecules are held together by some force of attraction, that is called as van der Waals force of attraction. You can just observe your notes which I had given for the definition of van der Waals force of attraction, that is weak intermolecular force of attraction by which different molecules are held together. Now the next thing is you have to discuss the types of van der Waals force of attraction. Under that, the first interaction is the dipole-dipole interaction. While explaining the Definitions of polar and nonpolar molecules. I had already told you which molecule exhibits the dipole moment. A polar molecule will always exhibit the dipole moment. So if you are saying a dipole molecule, then you should come to the conclusion that it is a polar molecule. So here also you will have a polar molecule. The interaction between the two polar molecule is nothing but dipole-dipole interaction. Now let me explain in detail by taking example. So you will always observe the dipolar nature in case of heterodiatomic molecules. Let me take HCl as the example. I have already explained, since Cl is the more electronegative atom, the shared pair of electron will slightly move towards the more electronegative atom. Not completely, slightly the shared pair of electron move towards more electronegative atom. So this gets partially negative charge and the hydrogen gets partially positive charge. Now consider another polar molecule. The same molecule I am taking, HCl. The same thing repeats here also. It's partially negative and partially positive. Now let me show the linkage between these two. On the chlorine you have partially negative charge. On the hydrogen you have partially positive charge. So negative and positive opposite poles attract each other. So here there is interaction between the chlorine and hydrogen. This interaction you call as dipole-dipole interaction. Clear? The second point you have to remember under dipole-dipole interaction is that they are the strongest force of attraction among the three types of interactions which comes under van der Waals force of attraction. This is about dipole-dipole interaction. The second one is dipole-induced dipole interaction. So here I already told you in the first case, dipole means it should be a polar molecule. Here induced dipole should be in the case of non-polar molecule. So what is happening here? A polar molecule will induce polarity in case of non-polar molecule. Let me take the example and explain you. For the polar molecule, take HCl as the example. You have slightly negative charge, slightly positive charge. I think you all know the example of non-polar molecules, homodiatomic molecules, Cl2, N2, O2, etc. Whatever, you can take any example. I am considering chlorine atom here, chlorine molecule, Cl, Cl. I have already told you between the homodiatomic molecules, the electrons are symmetrically distributed, or you can say at the center you have the shared pair of electrons. It neither move towards the first chlorine or it will move towards the second chlorine atom. It will be at the center because both are the same atoms. Means both have the same electronegativity. Hence electrons will be at the center. Now what happens? Here when these Cl2 molecules come closer to HCl, what is happening? Here you have negative charge. The electrons also negatively charged. So this negative charge and the negatively charged electrons will repel each other when they come closer to each other. So what happens is these electrons move slightly towards the second chlorine. So this chlorine becomes slightly or partially negatively charged. Since the electrons are moving away, this becomes slightly positive charge. Let me repeat this. You have non-polar molecule Cl2. I have already explained you. The shared pair of electrons are symmetrically distributed because both are having same electronegativity. So, here you have partially negative charge. Electrons, they are negatively charged. Negative repulsion takes place. electron starts moving away from this negative charge. So away antandre it's going to the second chlorine atom, towards the second chlorine atom. So this becomes partially negative and this becomes partially positive. You have negative charge, positive charge, opposite charges attracts. So you have some attraction between these two molecules that you call as dipole induced dipole interaction. So here a dipole molecule is inducing the dipole moment or dipole in the non-polar molecule. This is about dipole induced dipole interaction. The last one, the last interaction is induced dipole interaction, or you also call this as instantaneous dipole induced dipole interaction. As the name itself indicates, instantaneous dipole. At one particular instant, the molecules become dipolar in nature. Now, induced dipole or instantaneous dipole, induced dipole means both the molecules are non-polar molecules here. Here also non-polar molecule you have to take and one more non-polar molecule you have to take. Let me consider this by taking hydrogen molecule as the example for both non-polar molecules. So you can observe in a molecule both positive and negative charges. At some instant, at some particular point, what happens? The negative charges will come and occupy the space on one side and the positive charges occupies on the next side. What happens at one particular instant of time? The negative charges occupies one side and the positive charges occupies the other space. So, other side. This creates a dipole in the non-polar molecule. This is just an imaginary thing that you have to imagine at some particular instant of time. Negative charges will attain one side, positive charges will attain on the other side. So you have positive charges here. So the negative charges in this H2 will get attracted towards this side and occupies one side. This side will be occupied with positive charges. Now between this positive and negative, you have a kind of attraction or a force of attraction that is called as instantaneous dipole induced dipole interaction. Due to this instantaneous dipole which is happened by itself at some particular point of time, this is inducing the dipole moment or dipole in the other molecule. And this is the weakest force among the three types of van der Waals forces of attraction. So, by this we complete both hydrogen bonding and van der Waals force of attraction. Both are the weakest forces of attraction. Thank you.